I think I great. So welcome everybody. I'm very happy to be here today and to present some of the research of our lab in Politecnico di Milano. I'm an assistant professor at the Image and Sound Processing Lab at Politecnico di Milano. And the topic of today will be differentiable physical models of acoustic systems. So what we mean by acoustic systems, I will try to explain it in the introduction, and then I will go over some models concerning circuit models, then some delay networks, especially for artificial reverberation, and finally some conclusions. So what do we mean by acoustic or audio systems? So in this case, we are referring to multi-physics systems, whose physical domain generally interact in a potentially non-linear fashion. So you have multiple objects that might interact. You can refer to musical instruments, which might be acoustic or electronic instruments, or analog audio effects or amplifiers, audio transducers like microphones, loudspeakers, or also acoustic environment. Okay. So the idea is that we think that digital audio signal processing can greatly benefit from physical models of audio systems because, and they should be accurate models and also lightweight models that can run desirably in real time. But the real-time numerical simulation of the behavior of acoustic systems can be useful for many reasons. The first one is that once you have a physical model, you have also the interpretability of that model. So you can change parameters in such a way that you have an intuition about the relation between the digital model and the actual physical system. And also they can be useful to build compensation models that can modify the non-desired behavior of actual physical systems, actual physical audio systems, or they can be used to virtualize the behavior and or also to do prototypes of desired audio systems. However, developing models of this kind could be a problem in the context of digital audio signal processing because they might be very, very expensive. If you are targeting high fidelity simulations of audio systems, they could be very computationally expensive. And especially if you use physics-based methods, so model-based methods. On the other hand, data-driven models can be efficient, but you are going to lose some of the interpretability that we were mentioning before. So let me now jump to the concept of automatic differentiation. I'm sure that every one of you is familiar with this concept, but just to provide this concept better, let me just say that typically you have a neural network like this one with input X, output Y, and you want to estimate or optimize the parameters of this model by defining a loss function, which is characterized by a ground truth or measures or reference variable signals. And you want to minimize this loss function through a backpropagation process, typically based on the gradient computation. The idea of today is to not necessarily use neural networks, but arbitrary models, so arbitrary functionals or nonlinear functionals, and optimize their parameters using automatic differentiation based gradient descent methods. So we consider a physical system with known inputs, measurable observables or outputs, and unknown parameters. And the idea is that we want to find these parameters using automatic differentiation. The differentiation can be done in many ways, actually. So you can use numerical differentiation that might suffer from round-off errors, which might propagate and leading to instability. And it scales poorly when you augment, when you increase the number of inputs. You can also use, when you are able to do that, which is very nice in some cases, symbolic differentiation. So finding analytical expressions of the gradients, and but this might be cumbersome when you have a very complicated nonlinear system with multiple variables. So automatic differentiation is very useful because it's a completely data-driven and exploits the fact that routine computing f of x typically applies a sequence of elementary operations. So the composition of this elementary operation is exploited, and by computing the Jacobian of each elementary block, you can cascade all the Jacobians and exploit the chain rule in order to differentiate the whole model, okay? So once we have these tools at our disposal, the idea is to develop physical models which are hybrid, in a sense that they maintain a physically inspired structure. On one end, you are still retaining the interpretability and the robustness of a physical model. On the other end, you are exploiting the pairs of data-driven methods. So the accuracy, the adaptability. So these differentiable models open new paths for developing new kind of models, which are not necessarily neural networks, but are something in between completely black box models and completely or purely model-based, analytical models. In this context, we can exploit automatic differentiation engines that are widely used for deep learning, like TensorFlow, PyTorch, JAX, and so on. And so we are aiming to bridge this gap between these two classes of models. I will start with some examples related to circuital models, but before that, I will do an introduction about circuit models in general. So what is a circuit? So a circuit is something like this, okay? So for example, this circuit containing two BJTs is the circuit of the wah-wah pedal. And the idea is that, especially in audio signal processing, a very interesting field in this regard is virtual analog modeling, in which you have a reference analog circuit, like, for instance, a guitar pedal again, and you want to develop a plugin or whichever application which embeds a, let me say, a digital twin of that circuit, which should be as similar as possible to the original one, and also it should be able to run in real time. There are many, again, methods to approach these problems, which are mainly based on circuit simulation approaches like state space models, modified nodal analysis methods, Porter-Hamiltonian methods, or wave digital filters. Before going on, let me just fly over some concepts which I believe are very important in this context, which are, first, the difference between distributed models and lumped models. So distributed models are characterized by partial differential equations, while lumped models are characterized by ordinary differential equations. So in the first case, you have multiple variables which are discretized. For instance, time and space. You are discretizing time and space. In the second case, instead, you are discretizing just one variable, which is time. So, of course, there are some advantages and disadvantages in using one or the other kind of models, depending on the application that you are considering. And the choice on one of the two classes is the frequencies of interest of your model, the needed level of accuracy, the suitable level of the model computational complexity for the target application. And a very famous example, which is quite intuitive, is the transmission line. So the transmission line, or whichever waveguide you might think of, can be, depending on the context, modeled either using a lumped description, therefore a circuit, or a distributed description, which not only discretize the dynamics with the time variables, but also considering space as a variable to be discretized. And another important concept in this context, in my opinion, is the fact that we might always want to exploit physical analogies, which is there are some physical variables which are dual variables like pressure and velocity, voltage and currents, and can be always put in analogy, and you can always try to describe multi-physical systems using a common language, which is the language of circuits. So you can build circuit models of acoustic systems, of mechanical systems, and not just of electrical systems. A very famous example is this one, so the example of loudspeakers. Loudspeakers are multi-physical systems, and especially at low frequencies, they are often described using lumped models. This, for example, circuit, it is the TLS-small model, which is a circuital description of this audio system characterized by at least 3 physical domains. The first one is the electrical domain, and here is the signal, the electrical signal that you are going to produce with the loudspeaker. And then the mechanical part of the transduction process is described by this circuit in the middle instead, while the acoustic part is described by another circuit. And all these 3 subcircuits are coupled together, such that we can have a uniform description of the whole transduction process. So in general, a circuit is characterized by 2 kinds of equations. The first one describing Kirchhoff laws, so how the elements are connected one to the others, and the other class is the one of constitutive equations, which describes how locally the elements of the circuit will behave, okay? Example of circuit elements, you can classify circuit elements in many, many ways, depending on the fact that whether they are linear or nonlinear, passive or lossless, or active, or memoryless, or with memory, so dynamic. And here are some examples of, for instance, the resistor, the capacitor, the generator, or a nonlinear element, which is the diode. And then you have Kirchhoff laws. So you can think about Kirchhoff laws as constraints which are dictating how the elements are connected. For example, you have current laws, voltage laws. Here are examples of series connections, parallel connections, and you can have countless examples of different topologies that you can create with these blocks. The problem of describing circuits when you have to implement them in the digital domain, when you use Kirchhoff variables, so voltages and currents, is that you end up with a system of ordinary differential equations which are implicit in the discrete time domain, especially if you are going to use stable discretization methods. You end up with systems of equations which cannot be implemented as combinations of input-output blocks which constitute an explicit structure. This means that you typically need iterative procedures to find the solution of those systems, and these, of course, might be not desired in digital signal processing applications in which you need a deterministic behavior and you want to predict how fast is the processing. Okay? here is a very short example of two stable discretization methods, like the backward Euler method and the trapezoidal rule method, that you can use to approximate time derivatives, which are in continuous time domain, into the discrete time domain. And when you apply, for instance, this trapezoidal or bilinear transform discretization to the constitutive equation of a capacitor, this one, you end up with a discrete time domain equation which relates the two port variables, which are the port current and the port voltage, at the current sampling step in an instantaneous way. So which is the input and which is the output of these two variables needs to be decided. And as you can imagine, when you connect multiple blocks with this kind of relations, you will end up with a structure which has multiple dependencies, which are called delay-free loops, which are implicit equations that need to be solved at runtime. So all these methods based on the Kirchhoff domain and based on stable discretization methods use iterative solvers like the modified nodal analysis, sparse tableau methods, state space methods, and Porter-Newtonian methods. Today we will see a very brief discussion of another kind of method, which is with digital filters.
One question, one clarification, if I can ask.
Sure.
When you refer to the iterative methods, are you referring to the iteration over time, or are you referring to calculate a point in time?
Exactly.
You need to do the iteration of some optimization procedure.
Exactly. When you freeze one sampling step, and at that sampling step, you need to find the solution of the system. Otherwise, you are not able to find the output that you need.
Yeah. Okay. Yeah. Just wanted to clarify that. Thanks.
So thank you for the question. So another example of methods that instead are built with the intention to remove as many implicit equations as possible are wave digital filters. And they were developed by Alfred Petrice during the 70s to design stable digital filters starting from reference passive analog systems. And then they developed during the years and are still used today in order to simulate complex circuits which might be nonlinear in an efficient and robust fashion. So here is an example of a possible transformation of variables that you can apply when you use with digital filters. So you start from pairs of port variables, voltages and currents, and you go to another domain, which is called the domain of waves. So for each port, you have a pair of waves. One is the incident wave to the block, which is A. The other is the reflected wave to the block. So each element will be characterized by a scattering relation in which you have an input wave and an output wave. And also you are going to introduce in the new domain a free parameter, which is called port resistance. And the idea is that this parameter is completely free, so you can choose it as you wish. So the idea is that you are going to exploit this parameter in order to remove the implicit equations that you had in the Kirchhoff domain. For example, if you consider a Thevenin equivalent model, like whichever description of a one-port linear element, you will have two parameters, which are the bias voltage and the series resistance. And you have a constitutive equation, which is basically a line, okay? A line in the VI space, so voltage and current space. This line is transformed in another domain, which is the domain of waves, in another line, okay? This other line will be characterized by a slope and an intercept here. But you look at this slope expression. If you choose the free parameter, which is Z, equal to the series resistance, you are able to zero out this value, and you are going to remove the instantaneous dependence between the input variable A and the output variable B. So you end up with a very simplified expression of this Thevenin equivalent in which there is not anymore an instantaneous dependence between the input variable and the output variable. And of course, this allows you to remove implicit equations of your structure. Also, the Kirchhoff laws can be represented with multi-port structures that embed the topological information that you are wishing to describe. I will not enter into the details, but the idea is that whichever topology that you can imagine can be described with a multi-port junction with the multiple inputs and multiple outputs, which are your waves. So let's consider now the case of circuit characterized by one nonlinearity. Without, again, entering too much into the details for the sake of lack of time, I just say that whichever circuit characterized by one nonlinearity, like this one, which is characterized by one diode, can be represented with a structure which is completely explicit. Provided that you have a local scattering relation describing this element in an explicit way, all the whole circuit can be simulated using explicit relations. And this can be generalized to whichever nonlinearity, not just the diode. So here you have the nonlinearity relation in this block, and this topological junction models the whole topology of the circuit, and here you can connect whichever other linear structure. So this is completely explicit.
Alberto,
Yes.
got two different sorts of arrows. One of them which has that, which owns next to the edge of a box, and one that goes inside a box. You see what I mean?
Sorry, this I had to explain.
That sort of arrow, and then there's the other arrow going the other way, which doesn't have the thing inside.
This symbol here stands for the removal of implicit equations. So whenever I forgot to say here, like you see here, you have an arbitrary digital block characterized by this equation here. When you perform adaptation, which is setting the free parameter equal to the series resistance, you are removing the relation, you are removing the dependence of B from A. And this fact is represented by this stub symbol here. When you see this symbol, it means that at that port of that element, you removed the dependence between the input variable and the output variable. That's the meaning of that symbol. Okay. So in this case, we removed the dependence between the input and output variables from the side of the junction. You see that the stub is here. Instead, here we have removed the dependence from the side of this structure. So since this is linear, and this is linear, and this is a topological junction describing whichever topology, you can verify that all the delay-free loops are broke up, and so you have a fully explicit structure describing your C. Yeah. So fully explicit by digital structure. An extension that we did in the last years, that this was applying to one-port nonlinearities, so scalar nonlinearities, okay, was to extend this original theory to the case of multidimensional nonlinearities. For instance, two-port models like the BJT or whichever other two-port model. What happens if you use traditional wave descriptions and you connect, for instance, a BJT to a junction? The BJT will be characterized by two ports And these two ports are both connected to the junction, okay? Like in this case. You can make just one port using traditional digital filter theory of this junction reflection free. So you can zero out just one entry of that scattering matrix. But this will not be sufficient in this scenario to remove all the implicit relations. So you will have still instantaneous dependencies between the port variables at these two ports, okay? So this is a problem because it's preventing you to emulate these kind of structures with multi-port nonlinearities in an explicit fashion.
And that's due to the physics of the transistor, basically, the way.
Yeah, is related to the fact that in this case, not just the transistor, but whichever multi-port nonlinearity that you are going to connect to a junction will create implicit relations, okay? So you end up with these implicit relations, and you need to solve this in some way. So you are not able to provide an explicit representation of the circuit in this case. So what the idea that we propose is to generalize the definition of waves to vector waves. So basically, instead of using scalar waves, so applying one transformation for each port of the circuit, we are considering the two ports of interest, and we apply a transformation to both the variables, both the pairs of variables of those ports, and we define a a matrix of three parameters, which is in this case a 2x2 matrix, okay? So it's just a generalization to the vector case of the original transformation that we have seen, the original transformation of variables. This allows us to treat the two ports simultaneously as a vector variable, using vector variables. And in this case, we are able to remove the instantaneous dependence between all those port variables. And this allows us to simulate in a completely efficient fashion, explicit fashion, also circuits characterized by one nonlinearity, which is a multi-port nonlinearity, like the BJT, for instance. And I'm going to show you exactly the example of the BJT. So here is the symbol for the BJT, which is typically modeled as a two-port element, right? And this two-port element can be described in many ways, like using the Ebert-Small model, or this more accurate extended Ebert-Small model, which also has this pair of resistances here. And if you consider the equations, you have something like this, okay, in the Kirchhoff domain of voltages and currents. So the idea is that you can, in the digital domain, you have two options, right? So you have, the first option is this one. So let me go a step back. So we described the topological arrangements that you need to do in order to get an explicit structure. The problem which is left, which I forgot, is that this scattering relation must be an explicit one. Otherwise, if you given the input, you do not have the expression for computing the output, and also this local expression is an implicit relation, you are not able to compute the whole structure in an explicit way, right? So you also need locally a scattering relation which, given an input, gives you an output explicitly, right? So you have, in this case, you have an equation like this, which is an implicit one, yes.
what limitations does it have in practicality, like having a local, non-implicit relation?
It is exactly what I'm trying to address now. So this is the equation in the Kirchhoff domain, right? So voltages and currents. If you apply, it is an implicit relation. If I go to the domain of waves, in this scenario, we are still getting an implicit relation. So in principle, if you proceed with an analytical method, we are forced to use a local iterative solver. So we need a solver in this block, inside this block, which given this input, does iterations inside these blocks, inside this block, in order to retrieve, in order to find the local solution and return that solution as an output. Okay. And this is exactly what is done here when you apply the local Newton-Raphson method. So here is the derivation of the Newton-Raphson method. So you have the wave domain description with vector waves. I will skip all the mathematical details, but the idea is that inside the block, you have to iterate up to finding a solution. And once you find it, you return the variable, okay, using a scattering relation of this sort. But the alternative will be using a neural network. So this is an alternative approach. So you take, the idea is to locally model the BJT with a neural network, which is characterized, of course, by an explicit relation, V equal to F of A. And this becomes a local nonlinear regression problem, okay? So you are basically modeling the BJT as a small multi-layer perceptron, and you are going to construct a data set which is dedicated to the BJT. So you have you need just to collect data that are expressing the local relations between voltages and currents of the BJT. You can take those data and train a multi-layer perceptron. You define a loss function based on normalized mean square errors, and you get an explicit model for that.
So is the data, I assume it's simulated?
Yeah, you can collect those data in the way you want, also using SPICE, whichever tool, or you can iterate offline, collect data, and then train a neural network.
But if you're doing it, for example, in the Kirchhoff domain, you would need to have a description of all the parameters that you're gonna sweep through, and
Yes.
It's non-linear. So you just do it. Do you pre-generate the data, or do you stochastically do it as?
You can do it in many ways. What we do sometimes is to connect to the BJT to voltage generators or current generators, to the two ports, and drive those generators with white noise, for instance. And you do simulations for some seconds, collect data at multiple endpoints. So we are going to excite the nonlinearity in a proper way and collect a sufficient number of data, and then exploit those data to train the neural network. Okay. The nice thing is that you get a block which is reusable in many contexts, because basically this is can be used in many contexts. Is a more modular. Okay. Like in this case, the circuit that we have seen before is implemented using all the linear part below, and the root is the nonlinearity, which can be either explicit if you use the neural network, or implicit. If it is explicit, the whole structure is explicit. So you don't need any iterative solver. Here are some results which are verifying the accuracy. In both cases, you have very good accuracy, but in the case of the neural network, since you don't need any iteration, the real-time ratio, which is a measure of efficiency, is lower. So you have more efficiency. And in this specific case, since the real-time ratio is lower than 1, you are able to run that circuit in real time, okay? So in this case, is the advantage is visible, let me say. So we are trying to push in this thing, yes.
Did I spot that neural network is slightly less accurate?
Yeah, it was slightly less accurate, yes, because this really depends on how many data you train the neural network. So we can improve this, but this limitation was due to the fact that the neural network was trained with that data set, and the accuracy that we get is this one, which is still good. Okay, this is 10 to the minus. Sorry, the neural network is this one, not that one. So it is the neural network.
But you could improve that.
You could improve that, yes.
So very stupid question, but you said that you were mentioning that you could drive with white noise. This does not look like white noise. So then, are you saying that?
Or sweeps, you can also do sweeps with increasing amplitudes or increasing frequency. You can use many exciter signals to create the data set. So it's
But at the moment of your evaluation, are you doing?
no. In the evaluation, I'm just simulating the circuit. Okay. So
the whole thing.
So this is already the simulation of this original song. This. No, I don't find it. Anyway, I was showing the results of the simulation of this circuit.
The whole thing.
The whole thing. So
Okay.
the output voltage is reported here. Okay. The output voltage of the circuit. Okay, so now we are trying to push this thing forward, and instead of locally training a neural network for the neural element, we are trying to train the neural network together with the circuit structure. So we build the wave digital filter, and we plug to the root of our digital filter a neural network. And instead of training the neural network starting from the local input-output variables of the block, we are training the neural network starting from the input and output variables of the circuit. This means that when you train the neural network, you are also imposing the constraint of the actual circuit that you are aiming to simulate, okay? So you define an output variable and an input variable, which are not necessarily the input and output variables at the ports of the circuit, but they are the input voltage of the circuit, of the whole thing, and the output voltage of the circuit, for example. So the problem remains the same, but the structure that you are differentiating is not just local one, but is the whole thing. And here this is the formulation of the problem in which your direct acyclic graph of the automatic differentiation process is the discrete time simulation itself of the circuit, okay? So you are basically simulating the circuit during the training process, and you are trying to optimize just the parameters of the neural network in this way. And we obtained nice results with this approach. I will skip some passages here. We defined a slightly more complicated loss function in this case, along with the normalized mean square error that we used also before. We also used a loss function defined in the STFT domain, so in the frequency domain. But I think it is not worth entering into these details. The idea is that we also added a term here, which is a frequency dependent one. Again, we firstly implemented in Simscape our circuit. We built a data set, and then we trained the neural network in this a little bit stranger model, in a little bit stranger way. And again, the input and outputs now are the input voltage of the circuits, V in, and the output is V out. Here are the two approaches to which we are comparing our results. So in the first case, we consider the example of before. So the example in which we trained just locally the nonlinearity. In the second case, we are taking a fully black box model. So that take the circuit and express the whole thing as a neural network. Okay. And here are the comparisons. I don't think are so interesting, the comparisons. The nice thing, in my opinion, is that it works, in the sense that it is feasible. You can think also in these terms in which you are training the block while simulating the circuit. As far as the accuracy, in our case, we get a slightly lower accuracy, but you see that the behavior is fully described also with the method that we are mentioning. Okay, so let me move on. Yes.
Couple of questions. So first, what is the advantage in this case of like training within the wider circuit we've got memory-less element?
The advantages could be multiple, in the sense that now we are dealing with circuits which are completely known. Okay, but if you deal with the real circuits or real models, sometimes you know some parameters very well, but you are not completely certain about the values of those parameters. So the idea is that with this kind of approach, you are willing also to confine all the mismatches of the whole circuit inside the neural network, still keeping an interpretability and, let me say, applying constraints on the training that should allow you to be more flexible, but at the same time accurate. So in the neural network, also some other mismatches could be modeled, but they should be minor ones, and the neural network should be able somehow to compensate for that. That's the idea that goes beyond what we have actually done, but this is a promising experiment in my opinion.
Okay, so it's with a view to like hopefully like getting some things like experimental measures of
Exactly.
Okay. My only question was with the errors. Have you tried with like different seeds? Like what is more or less the variance of the errors? Like, do you find the networks in this case that they always converge?
It was
nicely. Yeah, or like the previous slide. I think
yes.
You had the mean absolute error. Like for those ones, like do you know more or less where are the standard deviations for observers? Like in the sense that do the networks always converge consistently to more or less the same error? Do you get very different results from like different initializations?
Okay, so this was a less standard approach. So we did many tries in order to get convergence, but once we found let me say a scenario in which it converges, then it converges in multiple configuration of parameters and inputs. So I would say that is a stable solution in that sense, comparable to the other two. Of course, the most stable one is the one in which you locally model the BJP, because it's in that case everything is very much is very controllable, it's very simple, the linearity is there, and everything is confined to that block. Okay, so of course it's easier to train.
Sorry, but
Yes.
Did you? I think you said that in this second version, the rest of the circuit is fixed.
Yes,
If there are
exactly.
any errors, that's kind of soaked up by the training of the network.
It's not the case here,
Right.
but with this approach, you could do that. Instead of having just a model, you have a real circuit with a schematic in which you have the values of the parameter values of each element. Of course, they are going to match the circuit, but not exactly. You might have small mismatches, for instance, in the resistance values and so on and so forth. And so the idea is that with this approach, you are also going to compensate for those mismatches.
Right. So that's what I thought. My question is, could you also, because it's very similar to circuit design techniques where you would be optimizing for the circuit components themselves, could you do that too?
It's exactly the next topic.
Sorry.
No problem, no problem, no
Go
problem.
on. Yeah.
So on this table, where is the performance of the iterative solver? So is the iterative solver?
It is not there anymore. It was compared before with the local neural network. Here we are comparing the structure which was trained the circuit along with the neural network. The case in which you locally trained the BJT, which was the first example, and then a neural network modeling the whole circuit. So taken from the literature. So you just model the whole circuit with the one neural. So the comparison here is between these three methods.
But my question is it worth doing a training where the behavior of the iterative solver is the ground truth that you use to train the neural network?
It might be, but in this case, you are independent from the kind of data that you have. They might be measures of the real circuit. They might be simulated data. So that, I mean, that's not the point here. Of course, it might be interesting, but the point is that here you can take a circuit and just measure the input voltage and the output voltage, and you are building a model of the circuit. So another advantage of this approach is that you don't always have the possibility to actually go to the two ports of the BJT and measure the voltage there. If you have a real circuit, it's much easier to take the input and the output of your pedal, for instance, and train the model starting from those data instead of going exactly to measure the voltage of the BJT. You see what I mean?
Yeah, but in these approaches, unless you do the iterative solver as a ground truth, there's a little bit of entanglement between the expressivity capacity of the neural network to reach the same.
The ground truth is from Simscape here. Is
I
at this price.
I understand that. It's just that there's this is what I'm saying makes sense. It makes sense in my head. It's that we know that this is a numerical approximation problem, even with the iterative solver. So does the neural network have the capacity to match the iterative solver if that is the ground truth? Not like the simulated.
But it's not the ground truth. The ground truth is spice.
I know,
So
I know.
the idea is that in our experiment is spice, but it could be a real circuit. So spice is playing the role of the real circuit, okay? So from that, you take the data, which are measures, okay?
Yeah.
And then the iterative solver is used in the specific example just to solve the local nonlinearity, just to solve the scattering relation of the BJT locally, okay?
We should move on, but I think by definition, there's three possible ground truths. And this experiment, this specific table compares only against one of them?
I would say that the ground truth is in our scenario just one, which is I'm emulating the measurement of a circuit. Okay. If I assume that my real circuit is the one simulated by SPICE, this conceptually works. Okay. Because SPICE is not interacting with my developed models. Right? You see what I mean?
Yeah, I just think that there's another ground truth at least. But yeah.
Okay, we can discuss it.
Yes.
Okay, have a nice discussion later.
So now we try to push again forward this approach, asking ourselves, is it possible to exploit similar methodologies to solve circuits containing multiple one-port or multiple nonlinear elements in a fully explicit fashion? So the idea is that our block might contain multiple nonlinearities. So far, it were one-port nonlinearity or one multi-port nonlinearity. What if I collect all the nonlinearities in one single block? So the first step is to generalize the definition of waves to n ports. So it's not just 2 ports, but an arbitrary number of ports, and define a new transformation which is n-dimensional. So the idea is that with this extension of wave variable definition, we can, for instance, model 2 BJTs, like 2 + 2 ports, 4 ports for the nonlinear block. Okay. So again, we are going to solve a nonlinear regression problem, which is more complicated, and we are going to model 2 transistors at the same time and putting both of them in the same block. So F is accounting for both the two transistors. Okay. Again, we use a multi-layer perceptron for this, and the data are obtained in SimScape. In some experiment, we use the SPICE, in some other SimScape anyway. And the example is the one of the wah-wah pedal, again characterized by this circuit with the 2 transistors, you see, Q1 and Q2, and then we develop a wave digital filter which can be represented in this way. You have this huge scattering junction characterized by many ports, and the 4 ports are connected to the 2 BJTs. So in this nonlinear block, you have the 2 BJTs, and all the other elements are linear. So we were able to do that, and by implementing the 2 BJTs with a neural network, also this circuit was emulated in a completely explicit fashion. Okay. So this is just to say that in principle, this approach can be extended also to accommodate multiple nonlinearities while keeping the linear part modeled in a white box fashion. Okay. And here is just the plot showing that the method is accurate, more or less as SimScape. And here comes what Mark was saying before. So why not applying this estimation procedure to compute, to estimate these circuit parameters, more in general, all the circuit parameters. So what we did are some experiments, and we published those. So all the results that I have shown are published. So if you are interested, I can point you to the specific papers. So the idea is that we want to estimate the parameters of the circuit starting from measurements, like in this case, with this bridge T network, in this case, it's completely linear. You have 1, 2, 3, 4, 5 parameters, and starting from the output measures and the input, you want to estimate the parameters of this system. So in this case, you can do that. You define the loss function based on normalized mean square error. And here is an example in which you start with some almost random random guesses. And some of them are already set to the correct value, but are left free to be changed during the training. So some others are not. We did many experiments. Here is a nice example which is showing that all the colored lines converge to the true parameter, circuit parameter values. Okay.
Anything interesting about those shapes that?
No, indeed. I mean, it's just showing that, for instance, here you always started from the same value for the 3 parameters, and they are going to find the correct solution, which were different ones. So you started from the same value, you reach the different ones. Sometimes you have multiple possible solutions which are correct.
So those lines that you have highlighted as dotted lines, is it fair to interpret them as local minima? Like,
No, these is the dashed lines are the correct values.
yes, sorry. So I mean more like the fact that all of them seem to start in the blue line, for example, like around where the blue dotted line is on the left.
No, this is the apex of the training.
Yes, but at the beginning you're starting, or maybe I'm understanding something that we're not saying, but you have all of these different colors at the beginning of the epochs, starting in the second value that you have there highlighted from bottom to top, right?
Yeah, exactly.
And then they find their way to their actual
Exactly.
yes. So is the reason why they start there because there's now a
Because we initialized them there.
you initialize them there? Okay.
Yes. It was a guess,
Got it.
a
Okay.
simulated guess. Okay. Okay, so let's try to apply this approach to a real audio system. For example, a MEMS loudspeaker. So here is a small size speaker, which is modeled with this circuit, similar to the one we have seen before for electrodynamic loudspeakers. And we apply this circuit parameter method in order to, okay, the input of the circuit in this case is an electrical signal. The output is a pressure signal. Okay, so the pressure measured with a microphone. And the idea is always the same. We are willing to exploit firstly some analytical formulas that are available in the literature to describe these kind of systems. Of course, they are not always super accurate. So the idea is to start with those formulas and then try to match measured sound pressure level curves in order to optimize the parameter to match these measured curves. So the idea is this one. So that we use the impulses. Like here, the input was an impulse. The output was the pressure. So input and output seeking, input and output measurements allowed us to exploit this loss function. In this case, we used a frequency domain and one loss function. So it's an error, an absolute error, a weighted absolute error between the measures. And this is the weighting coefficient. I will not enter into details otherwise. Here is the setup that we use to measure this MEMS loudspeaker. Okay, This is the loudspeaker, this is the microphone. And we use the audio precision for the measurements. And just to have an idea, here is the curve before the training. And after the training, we matched very well the measured curve. So it seems a promising approach. Where can we use? So these are other curves for different amplitudes, and or are more or less matching the measured curves. I would say that they are going to match very well in these, especially in these frequency range, but also at the resonance range, they are very good. So when can we use this kind of approach? For instance, we are working a lot on these compensation algorithms. Like, for instance, if you consider a loudspeaker, which is the pink physical block, this is a real loudspeaker, right? Like the MEMS loudspeaker. If we are able to derive an accurate model for that loudspeaker, we can exploit the circuit theory theorems that I will not discuss today to derive analytical inverse models of circuital descriptions of audio systems, and we can exploit those to virtualize the loudspeaker in the way we prefer. So the idea is that if this digital discrete time block is the exact inverse of the real transducer, these two blocks give you the identity operator. So because this is the exact inverse of this. So the third block here is the target loudspeaker that you wish to have. For instance, it might be a linearized version of this system. So you can apply non-ideality compensation algorithms with this chain in a very effective way. So for instance, you can linearize the actual loudspeaker, you can equalize the response of the loudspeakers by relying on this chain in which the output of the target system that you would like to have will be ideally equal to the output of the real system, because these two blocks simplify, okay, to give you the identity of it.
In this definition, how much do you assume that the target system, that your idea of digital twins, is that, are we talking about like a digitized version of the physical system, or are we talking more
Exactly.
about blocks?
For instance, this is the inverse circuit model, like the one we have just seen of the MEMS loudspeaker. This is the actual real MEMS loudspeaker. If this is exactly the inverse of this, I can impose the behavior of a target loudspeaker, which might be a virtual one, one that I want, like the linear version of the analog one, or the differently equalized version of that, and so on and so forth. Was a question? No. Okay, so I finished the first part. There were a lot of questions, so I don't know what we want to do. So I can go over the second part. We can stop here, have the break. I don't. Let's decide together.
Well, we do have to take you for lunch, Alberto. So
Sorry?
we do have to take you for lunch. How long is this second?
It's more or less as the first one.
So we would have to not interrupt very much.
As you prefer. I can try to.
I will not ask any questions.
If you are interested here, I'm going to talk about artificial reverberation. So delay networks for artificial reverberation. I can try to be faster.
Yeah.
And if you want to
do, if we can finish the
specific questions, we can do them at the end. Just so I go over them. Okay. So the context is the one of artificial reverberation. Every one of you knows about this, so I will skip this introduction. It is interesting for virtual reality, mixed reality, augmented reality. The idea is always that you want to recreate the reverberation of a specific environment, but you want to simulate it in a very efficient fashion, and you want to have very flexible models in order to simulate that reverberant behavior in an effective way. You have many possible solutions to this problem, at least 3 classes of methods, physics-based methods like wave-based, finite difference time domain methods, boundary element methods, image methods. You have measurement-based methods, like you take the impulse response of a theater and then you convert your signal with that impulse response. Or you have these delay networks, which somehow intersect with physical-based methods. But the idea is that they are designed to be fast. They are designed to have a very low computational complexity, but historically they were not so accurate. The idea was to match some specific measures of the reverberation behavior without being without matching the target impulse response. But the idea is that with this approach of differentiable models, we are aiming to keep this efficiency, this low computational complexity, while increasing the accuracy of these very models. For instance, a class of delay networks is the one of interpretable networks, which are characterized by this structure. You have multiple parameters, multiple gains. You have a feedback loop here with a feedback matrix A. And you can describe this structure with a state space, generalized state space model with non-unitary delays. So these are non-unitary delays. Okay, and I mean this is a very simple simple description, which can be thought of as a infinite impulse response filter, IIR filter, which is characterized by a very few number of parameters. Of course, this is the structure of a generic input response with a direct sum, early reflections, late reverberation. And with this kind of structures, we can do something like this. So you have samples that propagate in the delay lines. Here, we are assuming that all the coefficients are the same. And you see that at the output, you have these delayed impulses that are aiming to simulate the impulse response. And as long as time goes on, so the input was an impulse here, the impulses at the output are more dense, right? So this is modeling the late reflections, the late reverberation part of the impulse response. So this GIF allows you also to see how much the complexity increases as long as the original sample is fed to this structure. Okay. These kind of models dates back to Jotunheim's general FDM methods, and they boil down to comb filters if you define the parameter in a very simple way. So these are structures that are very old in the audio signal process. How to choose these parameters? In the recent years, some new solutions came up, but usually they were optimized using genetic algorithms. So the very heuristic procedures were used to match specific metrics of the impulse response, like the T60 or some specific reverberation time and so on. Okay, so the idea is therefore to develop differentiable feedback delay networks in order to optimize those parameters using tools similar to those that we have seen before for circuits, right? So the first question that we have to ask ourselves is this kind of structure differentiable? The answer is yes. So this structure is differentiable. The only thing that we must pay attention to are delay lines. Because if we implement delay lines with buffer without, that operation is not differentiable. But we propose this alternative solution, which is the one of expressing fractional delays in the frequency domain. So in this paper, you can find an implementation of an arbitrary fractional delay, di, based on this chain of operations. So you first perform the FFT of the input signal, you apply the delay, and then you compute the inverse of FT. This delay is basically a complex conjugate symmetric structure in the frequency domain. And this ensures you that when you go back to the time domain, you get a real signal, okay? Then you can apply some constraints to the parameters of the delay network. For instance, the matrix A for energy preserving reasons should be a unilossless matrix. So the feedback matrix A is usually set to be the product between unilossless matrix U and the diagonal matrix gamma, where you have attenuation coefficient. And there are ways to impose the unilossless process property, like exploiting this formula. So the idea is that you have some constraints to apply. So you are not directly learning these, which are the parameters of the feedback delay networks. You learn some unconstrained trainable parameters. You apply the constraints, like absolute values to keep the values positive, or some other parameters, and then you plug the constraint parameters to the FDN. Okay, so how to define the loss function? This is the most interesting part. You can define the loss function based on the energy decay curve and the echo density profile, for example. Like the energy decay curve is defined in this way as a backward integration, and shows you how much the energy is attenuated over time. And also the echo density profile is based on basically a measure of the local density of the impulse response. And this metric is characterized by an indicator function, which interestingly is not differentiable. So we defined this soft differentiable version of the indicator function, which is based on a scaled sigmoid. So this scaled sigmoid is characterized by a coefficient which multiplies the input x, and the higher the coefficient x, the better the approximation of this sigmoid is to the indicator function. So is as an example in which you increase kappa, which is the coefficient, and the higher the coefficient, the better the approximation to the indicator function. And this allows us to use this differentiable operation during training. You have a single input, single output FDNs that can be augmented with these filters. So these filters allow you to describe also frequency dependent behaviors. And you have also sometimes this correction filter term. Okay, so the idea is that when you introduce these filters, you can also, I will go fast here, you can also, this is interesting, model frequency-dependent behaviors. Like here we are introducing a term in the loss function, which is called the energy decay relief, in which basically you have, instead of considering the energy decay curve of the impulse response in the time domain, you consider the impulse response band by band, so in a frequency dependent fashion, and you, instead of taking the frequency axis within Earth, you take the MEL scale here, but the concept is the same, and you are going to match the decay at each frequency. So this allows you to get more accurate results when you train these kind of models. And here are some examples in which we see that the energy decay curve is matched, and also the energy decay relief is matched at multiple frequencies. You see that this is referring to a specific frequency of 121 Hertz. In one case, you are considering the loss function with the frequency dependent term, and in the other case, which is this one, and in the other case, you are not considering that term. So you see that the fitting here, for example, is far less accurate with respect to the ground truth. Here are other examples. I will go fast with this. And here are some images of the energy decay relief. Like the target is this one, and we see that when you have frequency-dependent terms, you get better matches of these images. A nice thing is to extend feedback delay network to the MIMO case. And I believe that this is the most interesting part of this presentation, because in my opinion, it's very promising in the sense that with differentiable models, we have the opportunity with these FDNs or delay networks in general, if we apply them multiple inputs and multiple outputs, we basically have access to a compact description of the sound field in an environment. Like if you think about a multiple input, multiple output FDN, you are thinking about scenarios like this one, okay? Like this one, in which you have, for example, 2 loudspeakers in the room and 3 microphones, okay? So the inputs are 2 of the FDN and the outputs are 3 in this case. And you are fitting in the same structure the propagation behavior along with the reverberation of all these channels here that are connecting the loudspeakers with all the microphones. And all this information will be embedded in the same filter, in the same efficient filter, which is the feedback delay network. So we started doing some experiments in this direction. And for instance, here you can see that 3 of the channels between loudspeaker and microphones are matched. So the energy decay curve of the target is matched by our feedback delay network. And here is also the matching of the echo density profile. So it is quite promising in this sense. And as a further step forward, the idea is, can we approach the performance of space-time processing in this kind of structure? And I believe that this is really interesting. So are we able to model the energy decay for all the channels, to model the decay in the frequency domain, to retrieve the direction of arrival, for instance, of the source, So in other words, are we able to obtain channels that are characterized by a spatial coherence? So are we able to maintain the spatial information in all the channels of these structures? If yes, this is very promising because we have efficient models that, according to which we can also do space-time processing, like localizing sources or in general computing pseudospectra and so on and so forth. So we did the first experiments in this direction, like we used this data set in which we have measures of higher order microphones. Okay, like this is a conference room in which you have 2 speakers, and all the blue dots are positions of high order microphones. Each high order microphone is something like this, in which you have multiple channels, and starting from those channels, you can use techniques like ambisonics or whichever other space-time processing technique to get access to higher order spatial description of the sound. So as a first question, we asked ourselves whether we are able with the feedback delay network to model a single input, multiple output scenario in which the input is this one. So the signal coming from this point, one input, and the output are all the channels of an higher order mic. Okay, so all the signals that you measure from these capsules here. Okay, so this is a single input, multiple output system. I will not enter into the details of that. We have a DAFEX paper accepted discussing exactly this scenario. And just to have, so this is the single input, multiple output feedback delay network that I was mentioning. And here is just a brief result, which I think could be evocative somehow. This is the pseudo spectrum. So here you have the 2 angles of the space, the azimuth and the elevation. This is the target pseudo spectrum. And this is the pseudo spectrum that we obtained using the feedback delay network, which is quite close to the target one. And with this, we can, this representation, we can do many things like localizing the source and or having a first rough sound field estimation. Very last thing is, can we apply these methods also to another kind of delay networks, which are the scattering delay networks? How they differ from the feedback delay networks? They are more physics inspired in the sense that the first reflections in this context are modeled exactly. So you are solving the wave equation and you are basically defining your network as a network of tubes, which are characterized, each tube is characterized by one dimensional wave equation. So these tubes are connecting the listening point to all the walls from which the sounds are scattered. And the interesting thing is that you are modeling in these kind of structures the first or early reflections in an exact way. Okay, so you have a prior information on the geometry of the room, on the position of the source and position of the receiver, and according to this geometric information, you can calculate the early reflection in an exact way. After the early reflections, all the rest of the information is treated very much in a similar way to the feedback delay. So the nice thing is that you have a hybrid model, which is for some parameters very physically interpretable, for some others is not. And it could be promising also applying differentiable approaches in this context. And we did it. So we have also a LaTeX paper discussing these kind of approaches this year. This concludes my presentation. And just to conclude, I have this slide in which I recap what I have said. So we showed how local neural network blocks can be embedded in wave digital filters to accommodate nonlinear elements and model the whole circuit in a fully explicit fashion. We showed how automatic differentiation can be exploited to optimize circuit model parameters in a data-driven fashion. And then with delay networks for artificial reverberation, we showed that multiple input, multiple outputs, FDNs can be tuned in order to match perceptual characteristics of given room impulse responses, both in the time domain and in the frequency domain. And also we showed how to optimize single input, multiple output FDNs so as to model the impulse response of higher order microphones in specific environments. And finally, we said something about the extension of these methods to scattering with the methods. Thank you for the attention. I'm sorry for the long talk.
Making questions. I'm looking at you.
Well, I made a promise, right?
Has anyone else got questions?
I've got a few, I can wait like. Well, we don't delay everyone.
Okay.
I have a question, if I may.
Of course.
So for the feedback delay networks and the MIMO case,
Yes.
your results show that you can optimize a model for one location, and then you get the acoustic image using the music algorithm. So all of that is, all that is cool. My question is, to what extent is what the feedback delay network will learn, to what extent is generalizable to other locations? You have the big problem here of the multi-input in the sense that you define how many inputs, and then you cannot control that in a reverberant real-world environment. So what are your thoughts there?
This is definitely an open question. I mean, these are the first steps towards the connection between these different classes of numbers. Right? I will these two. Okay, so we are trying to, starting from the blue class, approach the green one. Okay.
But these are so different problems. When you have a circuit that is on the green side, you know what you're getting into, right? The circuit has.
You mean why is not the circuit? This is the class of methods that you use to simulate room environments, right?
I thought it was a wave digital filters.
No. It's wave-based is a different thing. A wave-based method for room simulation is not wave digital filters.
Yeah.
It's like finite difference methods that you can use to simulate rooms. Like in COMSOL, for example, you have the model of the room and you apply finite differences to discretize the whole space and simulate the behavior of the environment. And these are very, very computationally expensive. You might need to wait hours to get a solution, to get a simulation of the environment, right? Mm-hmm. So this is one class of methods, which is they are very accurate, but you cannot use them in real time. Another class of methods is the one of delay networks, which used to be not so accurate, but very efficient. Sometimes even more efficient than convolution, okay, which is the third class, the red one. So typically you go into an environment, you measure the impulse response, and the easiest way to do the reverberation filtering is to convolve your signal with that impulse response. A first step in a more accurate direction is simulating the whole environment. And a step in the right direction in which you have a filter which is more efficient than doing convolution are the delay networks, right? So we are trying to keep the advantages of delay networks, but fitting them in such a way that they behave similarly to physics-based methods. You see the point? That's there. But we don't have the whole solution yet.
Kind of a little bit like follow to that point. For scattering delay networks, let's say parameters optimized for two relatively close positions. Let's say the single input, single output case, and you have like two different instances of it where the output just has been moved a little bit. Okay. Does interpolation in the scattering matrix parameters have like stability and like any kind of like if you interpolate between those two scattering matrices, like do the points in between more or less resemble what should be, let's say, a point along the way, or is like
there are no, to the best of my knowledge, there are not systematic experiments in this direction, but it's very interesting. And I would say it's really feasible in the sense that these structures are built in such a way that the feedback matrix, for instance, always honors some properties which ensure stability. So in time-varying scenarios or in scenarios in which you need to interpolate between different models, this could be an advantage. But which is the best way to do that is not known.
I think
We can stop this.
you must be tired. So
Okay,
that's really
can go
great.
on
Thank you, fascinating for me. I hope everyone else enjoyed it too. So thank Alberto.